Lesson 3.5, Equation Solving and Modeling. In this lesson, we're going to use techniques we've discussed in the past to solve exponential and logarithmic equations using algebraic and graphic techniques. And then at the end, we're going to go through an application problem involving Newton's law of cooling. Example 1, we're going to solve this exponential equation algebraically. We have 20 times the quantity 1/2 raised to the x divided by 3 power equal to 5. Okay, so first thing we want to do is isolate this base and exponent by itself. So we divide both sides by 20, leaving us with 1/2 raised to the x divided by 3 power equal to 1/4. Again, this is where you have to be a little creative because we're trying to rewrite it so the base on the left and the base on the right are the same base, because if we get those bases the same, then we can create a new equation where the exponents are the same. So we're going to leave the left side the way it is, 1/2 raised to the x divided by 3 power, and we're going to rewrite the right side of this equation as 1/2 raised to the second power. We're going in the reverse order using exponent properties. If we would redistribute this exponent through, we'd have 1 squared, which is 1, and 2 squared, which is 4. Reason we did that, now our bases are the same, so we can create a new equation where x divided by 3 is equal to 2. Multiply both sides by 3, so you get x is equal to 6. So that's solving an exponential equation algebraically. Example 2, now we're going to solve an exponential equation graphically. This one, if we tried to solve it algebraically, is actually really complicated. So we're just going to use a graphing calculator to gain a approximation for this x value. So what you would do is use your calculator, go to your graph, in y sub 1, type in e to the x minus e to the negative x divided by 2, and then y sub 2 is going to be equal to 5. And then what you're going to look at for your graph is where those two equations intersect. So you go second, trace button, option 5 is intersect, and you would find where these intersect, and you get that x value to be approximately 2.31. Example 3, now we're going to solve a logarithmic equation. In this example, we're going to use an algebraic method in order to solve this. So we have the common log of x squared equal to 2. So to solve this, we could rewrite this in exponential form. The base on our logarithm is 10. So this is the same as 10 squared equal to x squared. 10 squared is 100. And then to get x by itself, we would just take the square root of both sides. So we get x is equal to plus or minus 10. So if you put 10 in here, it's going to make this equation true. You put negative 10 in here, it's going to make that equation true as well. We could also solve this using a different method algebraically. So we have log base 10 of x squared equal to 2. On the left side, we could use our power property in order to bring this exponent down as a coefficient. So this would become 2 times log base 10 of x equal to 2. And then if we divided both sides of this equation by 2, we get the common log of x equal to 1. So now if we rewrote this in exponential form, we would get 10 to the first, which is just 10, equal to x. And if you notice, we get two different answers. Well, kind of. On the left side, we had two answers, plus and minus 10. On the right side, using this method, we only get a result of positive 10. We cannot use that method using the power rule when solving this logarithmic equation, because when we go through that process, we get rid of that result of negative 10 when we simplify. Because we had an x squared when we use that power rule, now that becomes a value of just x, which limits our domain to all positive numbers, whereas x squared would be all real numbers other than 0. So a little bit of a trick, things we have to be aware of with domain. This is the process we have to use on the left side in order to solve that, because then we get both of our solutions. If we use the method on the right, we would only get one of our solutions. Example 4, now we're going to solve a logarithmic equation graphically. Looking at this, fairly complicated, so we're just going to graph this and find out where these two intersect. So in y sub 1, we could type in the natural log of 3x minus 2 plus the natural log of x minus 1. And then for y sub 2, we would just type in 2 times the natural log of x. So again, you would graph both of these. You would go to second, calculate, option number 5, intersection, find out where these two graphs intersect, and you get an x value of 2. The last thing we're going to discuss in this lesson is Newton's law of cooling. You can see the formula down below. We have some main parts. T of T is equal to the temperature at time T. T sub m is equal to the temperature of the surrounding medium. And then T sub naught or T sub 0 is the initial temperature of the object. Okay, so what Newton's law of cooling does allows us to determine how long an object takes when placed in an environment that has a different temperature to reach the surrounding temperature. Or vice versa, if we know the time that the object's been placed, we can use this formula to determine the temperature of the object. So example 5, Newton's law of cooling. A hard-boiled egg at temperatures 96 degrees Celsius is placed in 16 degrees Celsius water to cool. 4 minutes later, the temperature of the egg is 45 degrees Celsius. So we want to use Newton's law of cooling to determine when the egg will be 20 degrees Celsius. So we have our formula from before. Some key pieces of information: the initial temperature is 96 degrees Celsius, and the temperature of the surrounding medium is 16 degrees Celsius. So using that information and the fact that we know 4 minutes later the temperature of the egg is 45 degrees Celsius, we can start plugging some of this stuff into the formula. So the temperature at time t is 45 degrees Celsius, equal to the temperature of the surrounding medium, which is 16, plus T sub naught, which is 96, minus 16, that would be 80, times E raised to, we know our T value was 4 minutes, so we could put 4 in for T, and then we still have our constant K. So the first thing we need to do is solve this equation for that constant of K, and then once we have that, we can use that constant in order to actually answer the question. So now if we simplify, try to get this isolated by itself, subtract 16 to the other side, so you'd have 29 equal to 80 e to the negative 4 times k. Next, we would divide both sides by 80, so you get 29 over 80 equal to e raised to the negative 4 times k. Now we're trying to solve for k, that constant. We need to get that out of the exponent. So since we have this exponential e, we know the inverse is the natural log. We can take the natural log of both sides of this equation. So the natural log of 29 divided by 80 equal to the natural log of e to the negative 4k. The reason we do that, the natural log and e, they're inverses. So we have the natural log of 29 divided by 80 equal to negative 4 times k. And the last step, divide both sides by negative 4. And now you would just type that in on your calculators to get an approximation. And when you do that, you get k is approximately 0.254. Now we're going to have to use that constant and the other information from before in order to solve for the problem. Use Newton's law of cooling to determine when the egg will be 20 degrees Celsius. Now we're going to use that approximation we came up with for K and the fact that we know the temperature we're looking for, or the time we're looking for when the temperature is 20 degrees, and the information we had in the beginning. We can plug that into our equation and now isolate and solve for T, the time. So the first step to do that, we would subtract 16 to the other side and get 4 equal to 80 times E to the negative 0.254 times T. Next, we would go through and divide by 80 and then take the natural log, and then we would have to divide by negative 0.254, very similar to the previous problem. So if you go through all the algebraic steps similar to what we did in the last problem and isolate for T, you get approximately 11.79 minutes. So when we started with that initial egg, it was 96 degrees Celsius, placed it in water that was 16 degrees Celsius. In almost 12 minutes, that egg would now be a temperature of 20 degrees Celsius. So that's using and applying Newton's law of cooling.